Welcome back to the video lecture series for the subject Deep Learning. This video covers the chapter 1 Autoencoders of Unit 5 Autoencoders and Generative Models. Let's start with what is autoencoders. Autoencoders are a special kind of neural network. Its main job is very simple. They receive input data, learn from the important features in the input data, reduce the input data with only important features, and then try to rebuild the input at the output layer. Here, reducing the input data with only important features is called as encoding, and rebuilding the encoded data at the output layer is called as decoding. So, autoencoders are a type of neural network designed to learn important features of input data by compressing the input into a smaller code and then reconstructing the original input is called as autoencoders. Think of it like a copy machine with intelligence. A normal photocopier machine just copies every dot on the page, whether it is useful or not. But an autoencoder is like a smart copy machine which asks what is really important in the picture. Can I store only the essential pixels and still recreate the full picture? So, let's now see how autoencoders work. For example, if I give the network an image of the handwritten digit 7, first the encoder part of the autoencoder compresses it into much smaller hidden form. We call this the latent representation or the code. This is like storing the important features, that is the slant of the line, the little crossbar, the angle. These are all the important features. Next, the decoder part takes this compact representation and tries to reconstruct the digit 7 as closely as possible. It may not be a perfect replica, but it will look very close. For example, another way to think about is like zipping a file on your computer. When you zip a file, it becomes smaller, but it keeps the essential information. Later, when you unzip, you get back the original file. So, autoencoders work in a similar way. They compress the data into smaller hidden code and then decompress it back. And here is the architecture of autoencoder. Basically, it is a feed-forward neural network, the same type of network we studied earlier, where data flows forward from input to output. But autoencoders have special middle section that makes them unique. This middle part is called as bottleneck. Think of it like a funnel. You pour in a lot of information at the wide end, but all the information must squeeze through a narrow passage before it comes out again. Because it has such a narrow path, the neural network cannot carry every tiny details. So it is forced to pick and keep only the most important features. This is the secret behind autoencoders, where the bottleneck forces the neural network to learn the essentials of data. An autoencoder has three main parts. One is the encoder code, which is called as bottleneck, and the decoder. So encoder, this is like a compressor. It takes the original input, say an image or text, and squeezes it down into a smaller form. Next is code. This is actual compressed summary that sits in the bottleneck. You can think it of as a short note or a shortened version of the data, storing only the key details. Next is the decoder. This is like the decompressor. It takes the short summary and tries to rebuild the original input from it. And suppose we give the autoencoder a face image. The encoder might compress the face into just a few numbers, maybe one number for eye position, another for face shape, and another for whether the person is smiling or not. The code is nothing but those few numbers, a very compact version of the phase. The decoder then takes only those numbers and tries to recreate the phase image. Of course, the recreated phase won't be pixel perfect, but it will look close enough because the autoencoder captured the important features. This architecture is powerful because it does two jobs at once. It summarizes the complex data and also it rebuilds data from that summary. Now let's see about the hyperparameters which are required to train the autoencoders. Training is done using mini batch gradient descent. That simply means instead of feeding the whole data set at once, we train the model at small chunks of data and updating weights step by step using backpropagation. But before training, we need to decide some key design choices that are hyperparameters about the architecture. Here we can see the four hyperparameters. First one is code size. This is the number of nodes in the middle bottleneck layer. If the code size is smaller, the autoencoder has to compress more, which forces it to learn only the most important patterns. In case if the code size is bigger, compression is less strict, but the model may just memorize the input, which leads to overfitting. The next hyperparameter is the number of layers. Autoencoders are not always shallow, they can be deep with multiple hidden layers in both encoder and decoder. More layers allow the model to learn more complex features, but they also make training harder. The third hyperparameter is nodes per layer. In the encoder, the number of nodes usually decreases layer by layer, squeezing the information into the code. In the decoder, the number of nodes increases systematically, expanding back to the original input size. So, think of it like a funnel that narrows down and then widens again. The last hyperparameter is loss function. We need to measure the reconstruction quality, that is rebuilding the input. For numerical data, we usually use mean squared error, which compares pixel by pixel or value by value. For binary data, we often use binary cross-dropping. So overall, these four hyperparameters, code size, number of layers, nodes per layer, and loss function define the shape and learning behavior of an autoencoder. Next, we will see the applications of autoencoders. First, autoencoders are used for dimensionality reduction, which is very powerful. They reduce large amount of data into smaller, meaningful forms. The second application is autoencoders automatically learn hidden features in the data. For example, if you train an autoencoder on lots of face images, the hidden layer may learn features like presence of glasses, smile on the face, head tilt, etc. These features are useful later for classification tasks. The magic is that the autoencoder learns them on its own, a programmer telling it what to look for. The third application is recommendation engines. This is something you see daily on Netflix, Amazon, or YouTube. Suppose you often watch comedy movies. The autoencoder compresses your watching history into small hidden code that captures your taste. The system then compares your code with other people's codes and recommends movies or shows that match your pattern. The next application is image recognition. When we stack autoencoders, putting several encoders and decoders on top of each other, they can learn more complex details in images. For example, the first layer may detect simple edges. This next layer may detect shape of the faces, and the next may recognize whole objects like a car or a cat. This layered learning makes autoencoders powerful in vision tasks. Next is anomaly detection. This is extremely useful in banking, cybersecurity, or even in healthcare. For example, if a bank trains an autoencoder on thousands of normal transactions, the model learns the usual patterns of spending. Now, if one transaction looks very unusual, say a sudden transfer of a huge amount to a foreign account, the autoencoder cannot reconstruct it well and flags it as suspicious. The last is image denoising. This one, it's a simplest thing. Imagine you have a old blurry photograph or a noisy grainy picture. A denoising autoencoder is trained by adding noise to clear images and teaching the network to recover the original. Later, when you feed in a noisy photo, the autoencoder can magically clean it up and give you a clear version. Now, let's see the special type of autoencoder called undercomplete autoencoder. In an undercomplete autoencoder, the code size, the number of nodes in the bottleneck layer, is smaller than the input size. So here in autoencoder, remember the code size will be smaller than the input size. In simple words, you give the neural network a lot of information, but you only allow it to store a tiny information in the middle. This forces the neural network to compress the data into a very compact form. So, but why we are doing this? Because if we give it a large code size, the network might just learn to copy everything blindly. So, if we give the code size smaller, then the network has no choice but to focus only on the most important features of the data. In other words, it prevents memorization and forces learning of the essential data. The idea of undercomplete autoencoder is similar to the principal component analysis, which also reduces data dimensions. But there is a difference. PCA can only find linear relationships, that is, straight line patterns. But undercomplete autoencoders also find non-linear relationships. That means they can capture much more complex patterns, which makes them more powerful. In short, undercomplete autoencoder is equal to bottleneck smaller than. It forces the network to compress data and keep only essentials. It is like PCA but smarter because it can also handle non-linear patterns. Regularized autoencoders. Remember how undercomplete autoencoders used a bottleneck to force compression. That worked because the bottleneck was smaller than the input. It means the hidden layers is smaller than the input layer. But if we build an overcomplete autoencoder where hidden layer is larger than the input layer, in that case the network becomes so powerful because it is with a larger hidden layer. Since the hidden layer is larger than input layer, it may just learn to copy the input into the output directly without compressing with important features. This is called learning with trivial identity function. Uh, this because the model is not discovering any deeper patterns. As an example, think of a student in the class. If you give them a very small scribbling notebook, they will try to take short notes, meaningful notes. But if you give them a huge notebook, they might copy the teacher's words exactly as spoken without processing or understanding. That's what happens in overcomplete autoencoder. The network learns the trivial identity function, meaning it just says, I'll copy everything from input to output. And that's not useful because the goal of autoencoder is to learn the essentials of data, not just to act like a photocopier. So, how can we fix this? We add regularization, which means adding rules or penalties during training to force the autoencoder to work harder and smarter. It means it's like forcing the student, don't just copy everything, pick the key points, summarize them, and ignore the unnecessary details. So, the purpose of regularization is to ensure that the autoencoder learns useful features from the given data, even if it has a large capacity, that is, larger hidden layer. The two famous types of regularized autoencoders are sparse autoencoder and denoising autoencoder. So, one type of regularized autoencoder is the sparse autoencoder. In this model, even if there are many hidden nodes, we only allow few of them to be active at a time. This is like having many light bulbs in a room but switching on only a few depending on the situation. This way, the neural network focuses on the most important features while ignoring unnecessary details. For example, when analyzing handwritten digits, only small group of hidden nodes may get activated for the number 3, but a different group of larger hidden nodes may get activated for the number 7. This helps the network discover unique features for each case. Here is the sparse autoencoder training and its benefits. Sparse autoencoders work by making only a few neurons active at a time. We train the neural network not just to copy the input but to keep most neurons silent. This is done either by giving a penalty when too many neurons are active or by keeping only the strongest few neurons active and forcing the rest of the neurons to zero. Here are few advantages of the sparse autoencoder. First, it prevents overfitting. Without sparsity, a big network might memorize the training data. So, sparsity acts like a rule, don't light up everywhere, be selective. So, as a result, the model generalizes better to new data. The second advantage is selective activation. Only the most relevant hidden neurons fire for an input. Each neuron tends to specialize, so only these neurons get activated. This leads to more meaningful features and often more understandable representations. The third advantage is data dependent routes. Different inputs activate different sets of neurons. For example, a cat picture might activate neurons for fur texture and pointy ears. A car picture might activate neurons for straight edges and wheels. This is called routing by sparsity, which makes the model efficient and robust. Another type is denoising autoencoder. Here is a very clever trick. Instead of feeding the network clean data, we deliberately add noise. For example, we take a clear image and blur it, or we add random dots here and there and give it to the autoencoder to reconstruct the original clean version. This makes the model stronger and more robust. It cannot simply copy the input because the input itself has noise. For example, in photo editing apps, AI uses this principle to remove grains or blurriness and give you a sharper picture. Similarly, it can also be used in speech denoising to clean audio recordings. And here are the benefits and applications of denoising autoencoders. First, robust filter learning. Since DAEs, in short for denoising autoencoder, are trained by adding noise to the input. The encoder learns to focus only on the important patterns and ignore the random noise. Next is identity function prevention. A normal autoencoder might become lazy and just copy the input to the output. That's not useful. But when we add noise, the model cannot simply copy, it is forced to actually learn the structure of the data. Third one is overfitting reduction. If a model memorizes training data, it performs poorly on new data. Adding noise during training prevents this memorization and makes the model more general. Finally, complex image denoising. Traditional filters fail when images are very noisy or complicated, whereas DAEs can handle such cases and recover cleaner images like restoring an old. So, where can we use denoising autoencoders? It can be used in image denoising, speech denoising, anomaly detection, and even data compression. And next type is stochastic encoders and decoders. Stochastic means involving randomness or probability. Imagine we give the autoencoder a noisy picture of the digit 7. A normal autoencoder just tries to directly minimize the difference between the input that is handwritten digit 7 and the expected output 7. Whereas a stochastic autoencoder tries to find what is the probability that this noisy input actually represents a 7 when decoded. The result may be like 70% chance to be it as 7, 20% chance to be it as 1, 10% chance to be it as 9. The training goal of the stochastic encoder is to increase the probability of the correct reconstruction, 7 in this case, and reduce the others. So in our case, there is 70% chance to be it as 7. So the training goal is to increase it to close to 100% while decreasing the probability of others. We don't just minimize a reconstruction error. Instead, we use something called negative log likelihood. The model is trained to maximize the probability of reconstructing the correct input from the noisy compressed code. Now, let's continue with decoder distribution examples. In stochastic autoencoders, the decoder doesn't just output fixed numbers. Instead, it outputs a probability distribution, and the type of distribution depends on what kind of data we are reconstructing. There are three cases. First is real values. If our data is continuous, or pixel brightness or temperature readings, the decoder often assumes Gaussian distribution. In this case, minimizing the negative log likelihood is the same as minimizing mean squared error. So it's just like trying to get the reconstructed value as close as possible to the real one. For example, reconstructing grayscale image pixels. Next is binary values. If the data can only be 0 or 1, like on, off, yes, no, then the decoder uses Bernoulli distribution. The probabilities come from a sigmoid output unit, which squashes the value between 0 and 1. For example, reconstructing black and white images where each pixel is either black 0 or white, which is 1. So next is discrete values. If the data can take multiple categories, not just two, then the decoder uses softmax distribution. Softmax gives a probability for each class, and the highest one is chosen. For example, reconstructing letters of the alphabet, where the output number be one of many discrete options. So to summarize, for real values, Gaussian distribution is being used. For binary values, Bernoulli distribution is used. And for discrete values, softmax distribution is used. Next is the limitations and structure of stochastic autoencoders. The first limitation is called the conditional independence limitation. This happens because many models assume that the output variables are independent once we know the hidden code. But in reality, variables are often correlated. For example, in an image, if one pixel is part of cat's ear, the neighboring pixels are probably also part of the ear. They are not truly independent. Modeling these correlations is possible, but it becomes computationally very expensive and slows things down. The second point is about stochastic structure. Unlike normal autoencoders, here both the encoder and decoder use stochastic or random functions. This makes the model much more flexible. It can capture uncertainty or variability in data. But it also adds complexity compared to simple deterministic inputs. So, to wrap this up, even though stochastic autoencoders can be heavy, sometimes inefficient, they're still very powerful because they provide probabilistic framework. This means they are excellent for handling complex and uncertain data. And the last title is Learning Manifolds with Autoencoders. First, what do we mean by manifold? Think of it like this. Although our data is stored in a very high dimensional space, say 28 by 28 image which has 784 pixels, the actual data doesn't use all those dimensions equally. For example, handwritten digits don't vary randomly in 784 directions. Instead, they vary smoothly in just a few meaningful directions like digits, slant, line, thickness, or position. That smaller surface inside a big space, what we called as manifold. So now, how do autoencoders help us to learn this manifold? The encoder compresses the input into latent code. The decoder then constructs the input from that code. But here is the thing: because of the bottleneck or regularization, the autoencoder can't just memorize every pixel. It's forced to capture the essential patterns that describe the manifold of the data. And here is the key principle. The autoencoder learns to pay attention only to valid directions or variation, the ways data can actually change while still staying realistic. It ignores irrelevant variations like random noise or meaningful distortions. In other words, latent code becomes like a coordinate system for the manifold, which gives us a compact way of describing complex data, which is super useful for tasks like dimensionality reduction, visualization, and learning good representations for downstream models. For example, if you train an autoencoder for MNIST digits, the model won't just memorize images. Instead, it will learn smooth directions call like make the stroke thicker, tilt the digit, or shift it slightly up or down. These are the true variations on the digit manifold. So that's all for this session. We'll continue with the next chapter in the next video.